Imagine a material that could become solid, liquid, or plasma, on command. No heat, no waiting, no chemical reaction. Just a seamless transition between states of matter, guided by precise energy control. This is the breathtaking concept of phase shift materials, and it might soon redefine how we build, travel, and interact with the world. At its core, phase shift technology is about controlling the arrangement and energy of atoms in real time. Every material has a point where it transitions between states. Ice melts into water, metal becomes molten, gas ionizes into plasma. What scientists are working toward is a method to manipulate those thresholds directly, letting us decide when, how, and why a material changes phase. It's a radical departure from passive materials that respond to nature. Instead, these materials would respond to code, current, or command. To understand this, imagine a car made of an adaptive alloy that can harden into armor when struck, then liquefy part of its body to self-repair scratches, and finally vaporize excess heat by shifting part of its surface into a plasma-like energy field. The same physical substance could perform all of that because its internal structure is programmable. The key lies in quantum-level energy control, using fields or laser pulses to alter the binding energy between particles. Researchers already have glimpses of this future. Smart materials today can change shape or stiffness based on heat or electric charge, like shape memory alloys or electroactive polymers. But those are primitive compared to true phase shift systems. The next generation will likely be built on quantum metamaterials, engineered lattices that can store and release energy on a subatomic level. Each unit cell in their structure acts like a programmable node, capable of responding to electromagnetic instructions. When millions of those nodes synchronize, the entire surface of a material can transform instantly. The implications are enormous. In architecture, walls could dissolve into transparent glass at dawn to let light in, then solidify into insulation by night. Emergency shelters could be airdropped as a liquid, then hardened into concrete-strength structures upon impact. Skyscrapers could shift their exterior coatings during storms, morphing into aerodynamic shapes to resist wind pressure. The physical environment itself would become dynamic, not static, a living infrastructure that adapts to conditions continuously. In medicine, phase shift materials could revolutionize implants and prosthetics. Imagine artificial joints that change rigidity depending on movement, or vascular stents that dissolve once healing completes. Microscopic medical bots made of these substances could flow like liquid through arteries, then solidify when they need to patch a rupture. Surgeons could operate with instruments that morph shape at the molecular level, offering unmatched precision and minimal invasiveness. In energy systems, the potential is even more astonishing. Power grids built with phase shift conductors could self-regulate, shifting between high-resistance and superconductive states to balance load. Nuclear reactors could contain plasma with walls that reconfigure phase to absorb radiation or reflect it. And spacecraft could carry hulls that transform for atmospheric entry, fluid for heat absorption, solid for impact protection, plasma-coated for radiation shielding. Each phase of the material would correspond to a functional mode of operation, like layers of armor evolving mid-mission. The science behind this begins with understanding phase boundaries. Atoms and molecules behave differently depending on how much energy they share. Solids are locked in a lattice, liquids move freely, gases even more so, and plasma, an ionized gas, contains enough energy that electrons break free from atomic nuclei. Traditionally, shifting between those phases requires changing temperature or pressure. But if you can manipulate atomic binding energy directly using quantum fields, you no longer need to heat or compress. You can simply tell matter what to be. A leading idea involves photonic control, using pulses of coherent light to excite electrons into specific states. When timed correctly, those electrons can either reinforce the atomic bonds or weaken them, effectively toggling the material between solid-like and liquid-like structures. Another approach involves magnetic phase induction, where strong localized magnetic fields alter spin alignments in crystal lattices, producing instant melting or solidification effects without changing bulk temperature. In laboratories, we already see fragments of this possibility. Scientists have created so-called programmable matter prototypes, microscopic particles that rearrange themselves to mimic different materials. These systems use electrostatic or magnetic interactions to change configuration. While still primitive, they prove that the concept is physically achievable. Imagine scaling this up: materials that can rearrange every atom to create real-time changes in texture, density, or transparency. The military applications, naturally, are both fascinating and controversial. Armor that turns fluid to absorb impact, then rehardens in milliseconds, could make soldiers nearly invulnerable. Stealth aircraft with adaptive skins could switch radar profiles or even absorb radar waves by shifting into plasma phase temporarily. Weapons might use phase shift tips that pass through barriers as liquid, then solidify inside the target. Even defensive shields could exist, fields of suspended plasma generated by surface phase transitions, forming instant energy barriers. But outside of warfare, the technology's creative potential could reshape civilization. Artists could sculpt living materials that flow and reform endlessly. Architects might design fluid monuments that shift shapes over time, reflecting human emotion or cultural rhythm. Fashion could transcend clothing altogether, phase-shift fabrics that change color, texture, and density like living skin. People could wear clothing that becomes armor in danger, breathable mesh in heat, or glowing aesthetic plasma for performance art. Transportation systems would benefit immensely. Phase-shift materials could lead to roads that reconfigure themselves for traffic conditions, or aircraft wings that reshape mid-flight for efficiency. Cars could compress themselves for parking or expand for comfort. Even submarines could phase parts of their hull into plasma for near-silent propulsion. The boundary between mechanical design and biological adaptation would disappear. Of course, such power comes with massive challenges. Controlling phase transitions requires extraordinary precision. A single error could destabilize a structure, causing it to liquefy unintentionally. The energy demand could be huge, at least until ultra-efficient quantum control systems mature. And there are safety issues. Materials that can vaporize or harden unpredictably could pose severe risks if misused or hacked. Cybersecurity for matter itself may become a new field, defending physical objects from digital manipulation. Ethically, this technology also raises philosophical questions. If matter becomes infinitely malleable, what happens to permanence? Would ownership or identity lose meaning when objects can transform endlessly? What would art, construction, or even individuality mean in a world where everything physical is fluid and programmable? These questions are not just theoretical, they will soon shape debates in law, ethics, and digital governance. Let's consider the environmental impact. On one hand, phase shift systems could dramatically reduce waste. Instead of manufacturing new products, you could simply reprogram existing materials to become something else. A phone becomes a cup, a wall becomes a chair. Recycling would happen at the molecular level. On the other hand, the energy to control these transformations might produce its own ecological burden unless renewable quantum energy sources evolve alongside it. The balance between innovation and sustainability will determine whether this technology heals or harms our planet. Looking further into the future, the integration of phase shift materials with artificial intelligence could lead to a new kind of living architecture, structures that sense their surroundings and respond intelligently. A building might feel the stress on its supports and reinforce itself automatically. A city block could liquefy partially to redirect floodwater, then re-solidify after the storm. This fusion of matter and intelligence hints at the ultimate vision: self-organizing, conscious material ecosystems. In this vision, our world ceases to be static. Every surface, object, and device becomes a participant in an adaptive network of transformation. Walls could communicate, vehicles could learn, and clothing could respond emotionally. Humanity would live in a reality of constant motion, matter dancing to the rhythm of information. The solid world becomes as fluid as data itself. To make this real, breakthroughs in several fields must converge: quantum materials science, nanoscale energy transfer, AI-driven control systems, and fusion-level energy management. Governments and corporations are already investing in early research through advanced materials programs. Within a few decades, we might see the first generation of fully controllable phase-shift composites entering aerospace or high-security applications. Consumer technology will follow once costs drop and control methods become safe. Some futurists even imagine a world where personal devices can create anything on demand. Instead of ordering products, people might command raw phase-shift matter to construct tools, furniture, or even food instantly. A handheld matter shaper could reorganize the atoms in a chunk of base material to produce any object with digital precision. The ultimate 3D printer, except it wouldn't print, it would transform. The line between digital design and physical creation would vanish completely. Education and art would evolve too. Students could study chemistry by interacting with live, responsive materials. Museums might host living exhibits that evolve over time. Even entertainment could change: concert stages that morph with the music, or films projected through shifting plasma screens that breathe with the story's emotion. But with all this excitement comes the responsibility to handle it wisely. Phase-shift materials will blur the boundary between science and magic, creation and destruction. The temptation to weaponize or commercialize without ethics will be immense. Humanity will need a framework for matter ethics, defining how we use, share, and respect the power to reshape physical reality. Imagine a world where cities adapt to climate, where space travel becomes routine through self-healing ships, where clothing and shelter respond to human need instantly. In such a world, energy and creativity replace scarcity and waste. The power to command matter becomes not just a scientific milestone but a philosophical awakening. We begin to see that the universe itself is not fixed, it's a dynamic system waiting for consciousness to learn how to mold it. Phase-shift materials might one day become the cornerstone of post-industrial civilization. When humanity gains the ability to rewrite matter itself, our societies, economies, and even definitions of reality will shift with it. From the smallest atom to the grandest structure, existence becomes programmable. And when that day comes, the phrase, "solid as a rock," will mean nothing at all, because solidity itself will be optional. The future will be fluid, alive, and endlessly transformable. The only true constant will be change, shaped by our will, guided by our wisdom, and crafted from the shimmering dance of atoms obeying human imagination. Hey everyone! If you enjoyed this video, make sure to hit that like button, drop a comment to share your thoughts, and subscribe so you don't miss any of our future uploads. Your support helps this channel grow. Thank you for watching.